jumping to section 3.9. Okay, we're jumping to the section 3.9. This is more application of derivatives. Application of derivatives, and there's a lot of applications of derivatives, because remember that a derivative is just instantaneous rate of change. How fast is something changing at any given moment? That's what a derivative really is. So if we can model something, if we can model, population growth, we can find the derivative of that equation to find instantaneously, like, okay, at this point in time, population was growing at a certain rate. And we can compare that to the rates at other times. And then we can say, well, what's the second derivative mean of that then? What's the third derivative of that? What's the rate of change of the rate of change mean, right? We have been using the physics application all along, where I say, okay, the derivative of speed of position is velocity, the derivative of velocity is acceleration, and we can use that. But now what we're going to talk about is, okay, what are other things that we can use? And how are these rates related to one another? Okay, so it's an application section. The book introduces it like this. Well, let's just jump to the example. Come on, get out of there, please. Thank you. All right. It's all word problems, this whole section. It's all word problems. Air is being pumped into a spherical balloon. We're assuming that it's sphere and not weird balloon shape. Air is being pumped into a spherical balloon so that its volume is increasing at a rate of 100 cubic centimeters per second. I don't know how we know that, but we know that. Its volume is increasing at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? I like to think of this section as like, if you have friends taking AP Calc, like this is like all they do. They're like always in this weird word problem mode and very, very theoretical about all this stuff. We're more algebraic. That class is a lot more theoretical. So this is kind of like a snapshot into what they do every day. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Notice how I give you like a moment. I say, okay, how fast is the radius of the balloon changing? So that's a rate of change, right? How fast is the radius changing? When the diameter is at 50 centimeters. Instantaneously, the diameter being 50 centimeters. Okay, what I love to do in these word problems is figure out what we know and what we don't know. So let's do that. Okay, we are told that the rate of change of the volume. Now, watch the notation here. I'm going to call that dV dt. That's the rate of change of the volume, right? The volume is changing per time, cubic centimeters per second. I see that right here, right? Change in volume over time, dV dt. Okay, it's changing at a rate of 100 cubic centimeters per second. We know that, we want to find the rate of change of the radius. Okay, I want to find dr dt, right? That's what we are looking for. We are looking for the rate of change of the radius, not the actual measurement of the radius. We're actually looking at the rate of change of the radius. How fast is the radius increasing? When the diameter is equal to 50. And when the diameter is 50, what's the radius? 25. I'm told what the radius is. I want to know when the radius is 25, how fast is the radius actually increasing? Right? When the radius is 25, how fast is that radius actually increasing? That's what we're looking to find here. Now, the hard part about this is that we're going to need to create or find some equation that links these two rates together, which that's the title of the section, related rates. I have two different rates happening, and they are related in some way. So let's figure out some sort of equation that ties them together. Well, if I've got volume and radius, don't I have a volume formula that has a radius in it? The volume of any sphere is 4/3 pi r cubed. I will give you any standard formulas that you need, like volume formulas, area formulas. I'll give you all of that. It's not like you need to come up with that in your brains. So there's our volume formula. Volume of any sphere is 4/3 pi r cubed. 4/3 pi r cubed. Okay, now I need dv dt, right? Not that I need. I know dv dt. I want to find dr dt, right? So let's differentiate this equation, right? Let's find the derivative of this equation, because on the left side, that's going to be dv dt, right? Or v prime, if you will, right? On the right side of this equation, okay, is pi a variable? No, it's a constant, right? It's a number. Okay, my only other variable is the radius on the other side. So let's differentiate that radius. Well, 3 times 4/3 pi r squared, right? Now, we are differentiating. What's on the bottom here of both of these rates? What's on the bottom? Time, right? So that's our x. Do we even see time in that equation? No, we are differentiating this with respect to time. So that actually means that we're kind of doing implicit differentiation here. Because I'm differentiating with respect to time. That's what's on the bottom of our rates. So if anything were to have happened on v, I would need to treat this as like an implicit differentiation. If this was like v squared equals, I would need to say 2v v prime or 2v dv dt. But since it's just v, I could just call that dv dt. Now, I'm still differentiating on the right side with respect to time, so I have to say 3r squared, and what goes here? Dr dt, right? Dr dt. Or if we're back in our old prime language, we would say 3/4 pi r squared r prime, right? Which is dr dt. R prime is dr dt. V prime is dv dt. Okay, now let's reduce that down a little bit. Come on. So that's dv dt is equal to, well, 3 times 4/3 is just 4. 4 pi r squared dr dt. You want to know something really cool? What is 4 pi r squared? Anybody know what that formula is? That's the surface area formula for a sphere. Really cool side note here, if you differentiate the volume formulas, you get surface area formulas. Interestingly enough. You differentiate any volume formula, you get a surface area formula. Okay, but that's besides the point. We don't even care about that right now. So dv dt is 100. 4 pi. When do I want to know? I want to know when the radius is 25. This gives us an equation that we can solve for dr dt. We differentiate. We know that r needs to be 25. We are given the moment when r is 25. Okay, so now we just solve for dr dt. All right, so that gives me, let's find that actual value. 4 times 25 squared, that's going to be 2,500 pi. So 100 is equal to 2,500 pi dr dt. And we're going to divide over that 2,500 pi. Really small number. 100 divided by 25. I should really put that in parentheses. 2,500 pi. There we are. So 0.0127. 0.0127. Is dr dt. 0.0127. Perfect. Okay, now what is that? That's the rate of change of the radius. Let's figure out what units we need to say. Okay, well, the linear length is centimeters, okay? And radius is a linear length, right? Radius is not an area, but a linear, right? So we are saying 0.0127 centimeters per second. 0.0127 centimeters per second. Think about what you found and say, okay, if the radius is changing that much, what is that radius? That radius is a linear length, not a two-dimensional length, it's a linear length. So it's centimeters, straight up centimeters per the time, per second. So that's how fast the radius is actually changing when the radius hits 25 centimeters. Okay. So just to kind of go back and think through the process one more time, we figured out what we knew and what we didn't know. We wanted to find the instantaneous time at which we needed to find whatever we need to find, right? I should have to give you a time. And then we tied those two rates together using a derivative, right? We had volume and we had radius, so we know this volume formula with the radius. Then we can say, well, if I differentiate both sides, taking into account implicit differentiation, we can plug in what we know and what we don't know to solve our problem. Let's do that again. All of these problems are unique in their own way, right? That's what's difficult about these related rates problems, is that each of them are their kind of their own thing. Okay, they all work in a slightly different way. Okay, a ladder, which is 10 feet long, rests against a vertical wall. If the bottom of the ladder starts to slide away from the wall, and it slides away at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall? When the bottom of the ladder hits 6 feet. Okay? Now, when doing these types of problems, I like to draw out a picture because that helps me understand how the rates are going to be related to one another. Okay, so we got this vertical wall, and I got this ladder. That is 10 feet. The bottom of the ladder starts to slide away from the wall, right? It starts to slide away at a rate, okay, there's a derivative, right? There's the rate of change, at a rate of 1 foot per second. Now, since this is kind of like a horizontal movement, I'm going to call that dx dt. Because the other one's going to be a vertical movement, I'll call that a dy dt. X component being left and right. So dx dt is 1 feet per second. And I know it's dt because, look, length per second, right? That's our rate. Length per time. How fast is the top of the ladder sliding down the wall? What do you think my notation is going to be here? dy dt, right? I want to know dy dt. That's our unknown. How fast is the top of the ladder sliding down the wall? What's the rate of change as the ladder slides down the wall when the bottom of the ladder is 6 feet from the wall? When x is 6 feet, right? That's what I want to know. So when x, I'll put this here, when x equals 6. That's enough information to solve my problem. Okay. Now, the first thing that I want to do here is figure out when the ladder is 6 feet away from the wall, how far is the ladder up the wall, right? That's the first thing I want to figure out. When the ladder is 6 feet away from the wall, how far is the ladder down the wall? Okay? Because we don't know where it starts, but we know where we want to instantaneously find. Well, That's Pythagorean, right? So 6 squared plus, we'll call that y squared, is equal to 10 squared. Because this ladder is a fixed length, right? That 10 foot's not changing. It's not like I'm going to make my ladder smaller as I go down. There's no like DZDT or DCDT, whatever. No, the length of the ladder is not changing. That is a constant length of 10. So let's figure out what my y component would be when my x is 6. So 36 plus y squared is equal to 100. So y squared is equal to 64. So y is equal to 8. Obviously plus or minus, but we negate the minus because it's real world. 8 foot. So this is the instantaneous moment. When x equals 6, y equals 8. That's when I want to find the rate of y. Okay, so now let's use that same Pythagorean formula to link the rates of x and y together. X squared plus y squared equals 100, 10 squared, right? That's an equation that links the two values together. And that, for some of you, is going to be the hardest part. Coming up with some sort of equation that links these two rates together. Whether it's Pythagorean or a volume or a rate, whatever it may be. I don't know. It's different for each one. Let's find the derivative of both sides. Now, look here. What's on our bottom? T, right? So when I go to differentiate the left side, when I go to differentiate x squared, I've got to write 2x times x prime, right? That's implicit differentiation. 2x x prime. Or in other words, 2x dx dt. Right? 2x x prime or 2x dx dt. Plus, same thing with y. 2y y prime or 2y dy dt. Now, what's it going to equal on the other side? What's the derivative of 100? 0. Okay, now, because think about it, like, is there any rate of change for that 10? Is my rate changing for my hypotenuse? No, my length isn't changing it's a fixed, right? It's a constant. That's why it doesn't equal anything. That's why it equals 0. Okay, now let's just kind of, oh, that's right. We need to solve for dy dt. Let's solve for dy dt over here. Okay, so we subtract the 2x dx dt. 2y dy dt is equal to negative 2x dx dt. We can divide by the 2's and divide by y. So dy dt is equal to negative x over y dx dt. Right? We divide by the 2, it cancels out. We divide over with the y, it's x over y dx dt. Okay, now we have enough information to solve for dy dt. Dy dt is equal to negative x over y. Well, we know what x and y are instantaneously, right? Negative x over y times, well, what was dx dt? How fast was the bottom moving? 1 foot per second. Times 1. So negative 3/4. Negative 3/4. Oh. Negative 3/4. And what is that negative 3/4? Well, negative 3/4, let's go back and look at our, feet per second, right? Linear length, right? Going down, it's not like feet squared per second. No, it's linear length, feet per second. It's going downward at a rate of 0.75 feet for every 1 second. When 6, 8, right? When x is 6 and y is 8. If I take that at any other time, well, it might be moving faster or slower, right? If I change that to when x is 7, well, then it's a little different because I got to calculate a new y value. But that wouldn't be very difficult anyway. I could quickly calculate a new x and y value, multiply by that dx dt, and that'll give me what my rate is for my y. Questions on that one? Let's take a look at another one. A water tank has the shape of an inverted circular cone. Ooh, inverted circular cone. Inverted circular cone. So that just means it looks like an ice cream cone, right? So here, there. That's open. So water tank has the shape of an inverted circular cone with a base radius of 2 meters. And a height of 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. So basically what I'm saying here is I'm going to pump water into this thing, and when it hits 3 meters, that's when I want to know how fast the water level is rising. Find the rate at which the water level is rising when the water is 3 meters deep. Okay, so I got my diagram drawn. Let's also say if water is being pumped into the tank at a rate of 2 cubic meters per minute. Okay, what is that? What is that? That's volume, right? And I'm talking about it in terms of a rate. So I know that dV dt, the volume is changing at a rate of 2 cubic meters per minute. Okay, what do I want to try to find? What do I want to try to find? I want to try to find the rate at which the water level is rising. Now, what's changing here in the cone when the water level is rising? What's changing? Is the radius changing? No, the radius is remaining constant, which is going to come back in a second. The radius is going to remain constant no matter how big or small or how much water goes in or out, right? What about my height? Isn't that how much the water level is rising? So that's what we're looking for. Okay. Now, volume for a cone is 1/3 pi r squared h. 1/3 pi r squared h. That's the volume of a cone cylinder, or cone formula. That's the volume of a cone formula. 1/3 pi r squared is the area of the base times the height. Times 1/3. Coincidentally enough, that's the same as the volume of a pyramid. 1/3 area of the base times height. The area of the base of a pyramid is just a square or some other shape. This is just a circle. 1/3 pi r squared times height. Now, again, this is a little weird here. Okay. I want to somehow tie in my radius with my height. Because while my radius at the top is remaining constant, think about the radius of the red, right? Think about the radius of the red. As the water level hits 3 meters, the radius is slightly smaller because it's down a little bit, right? The radius is slightly smaller in there. So it is changing at my red line. So maybe I need to get this radius out of here. Maybe there's some way I can get that radius to be in terms of height. Take a look at this. here, and here. I have similar triangles, don't I? You see the two nested green triangles in there? Those are similar triangles. Where this is, the top is 4. This here, like a ninja, sneaking up on me. That's like in a couple minutes here. The radius full is 2 meters, so the top length is 2. Right, that's set. That's not changing. And I want to know. And then I want to know how much this is. Right? What's my radius there? I know this is at 3, right? I know that this is at 3. But if I can change, if I can use this 2 and the 4, watch here. Watch. If these are similar triangles, I know 4 to 2 is the same thing as H to R. Right? 4 over 2 is the same thing as H over R. So if I want to solve this equation for my radius, I can do so. Cross multiply and divide. 4R is equal to 2H. So R is equal to 1/2 H. I know my radius is always equal to 1/2 my height, or H over 2. Okay, now how does that help us? Well, that's going to give us an equation that's going to remove R. Because if I go to differentiate this R, I'm going to need like a dr dt, right? If I go to differentiate that volume equation as it sits right there, I would need a dr dt. I don't have a dr dt. So I need to get that R out of the equation using only H's. You get that R out of the equation so I can have only H's in there. When I go to differentiate, it's only going to be a dv dt on the left side and a dh dt on the right side. And to do so, I'm going to plug R is equal to 1/2 H in. So there's going to be 1/3 pi times, I'm going to call that H over 2 because that's what I did in my notes. H over 2 squared times H. Now, V is equal to 1/3 pi times H squared over 4 times H. And let's reduce that all to say volume is equivalent to, looks like I've got H to the 3rd. I'll put pi up there as well. And on the bottom, I've got a 3 and a 4 to make it 12 altogether. Okay, now I'm going to differentiate. Now I'm going to find the derivative. Okay, so that means I've got a dv dt on the left side. On the right side, that's going to be a, let's call that 1/12 now, a 3 times 1/12 H, let's put pi in front too, 1/12 pi H squared dh dt. You follow me there? The 3 comes out in front because of the H to the 3rd. This 1/12 is just that divided by 12. I brought the pi out as well because, again, it's just a constant, just a number. I reduce the exponent by 1, and then I multiply on a dh dt. Okay, let's reduce that a little bit. So dv dt is, so that would be like a 1/4 pi H squared dh dt. Okay, I think I know everything now. dv dt is 2. Pi is pi. H, I want to know when the instantaneous height is 3. And dh dt is what we're looking for. So this was a 2, 1/4 pi times 3 squared dH dt. Okay, let's solve for dH dt. So this is 2 times 9/4 pi dH dt. We divide by 9/4 pi over to the other side. 2 divided by, let's put it like this, 9/4 pi. 0.283. So 0.283 is dH dt. And let's write it out as with the correct label. So this was meters cubed per minute. So height is a linear length. So it's just meters. 0.283 meters per minute. That's how fast the water level is rising when the height of the cone is 3 meters. When the water level is 3 meters deep. And that rate will change depending upon if I choose to do this at when it's at 2 meters. Okay, it's probably going to be filling faster because the radius is not so big. But then if I choose a little bit later on, if I said 3.5 meters, well, it's going to be filling a little slower because the radius is bigger now. So the water level is going to decrease its rate. Right? Okay. Let's pause there. That'll give us 2 questions to do tomorrow. Sound good? The goal for tomorrow is to finish those 2 questions, and then I want to let you have like the entire class period to work on tomorrow, but Thursday, to work on these problems from the homework set, because they take a little getting used to, and if you get stuck, man, you're stuck. So I want to give you a little bit of time in class, all the time in class on Thursday to work. You're going to have a little bit tomorrow as well. Let me stop the video.